Okay, this is lesson 8.2. Remember back in unit 7, we learned a few tests to determine if something converges or diverges. Something called the geometric series test, the alternating series test, and also the nth term test for divergence. Well, guess what? We're going to do a few more in unit 8. Today, or this video, I want to show you something called the integral test and the P-series test. So, looking at the integral test, it only works if the function f of x is positive, continuous, and decreasing for the x values greater or equal to 1. And then the terms can be converted to the function. What we're saying here then is that the sum of the terms in the series and the integral from 1 to infinity of the function either both converge or they both diverge. I'm not saying that the sum and the integrals are the same. I'm just saying we can show that if the integral converges, then the sum also converges. Or if the integral diverges, then the sum also diverges. Now, once again, you can only use this test if we're looking at functions that are positive, continuous, and decreasing. So you should always check for those things first before you go ahead and use the integral test. But since I've told you that these examples use the integral test, you should be able to say that yes, the function f of x in this case is positive, continuous, and decreasing. So what is the function f of x? Well, it would be 1 over x squared plus 1. I know this is always positive because x squared is positive. Adding 1 still makes it positive. I know this is continuous because there's no asymptote involved. And I know it's decreasing when x is greater or equal to 1. I can just plot a few terms, or you can take the derivative and show that it is decreasing. Now, what I should be asking you then is to evaluate the integral from 1 to infinity of this function. If this integral converges, I know then the series converges. If this integral diverges, then I know that series diverges. Now notice that this is an improper integral, so I'm going to introduce my variable here for proper notation. Let's take the limit of, I'll use the letter b this time, the integral from 1 to b now of 1 over x squared plus 1. I hope you know what this integral is. Think back to chapter 6. Did I hear someone say arctangent? You bet. This is arctangent x. We'll evaluate this from 1 to b, which means we'll put in the limit of b approach to infinity, arctangent of b minus arctangent of 1. Arctangent of b, where b is infinity, that's the same thing as pi over 2. Arctangent of 1, that's the same thing as pi over 4. This simplifies to pi over 4. So, what do you see? Well, hopefully you'll see the following. I should give myself some more space. I should say, I guess I should say first, since f of x is positive, continuous, I'm just using short form, okay, being lazy, and decreasing for all values of x bigger or equal to 1, and it converges, because that's what I just showed over here. Therefore, by the integral test, the sum of n equals to 1 to infinity of 1 over n squared plus 1 must also converge. There you go. So I kind of wrote out all the things you would do on a written response AP exam. This justification is what they're looking for. Okay? So I'm going to ask you to try number 2. It's pretty much the same kind of idea and setup. hope you remember how to do some integrals. So go ahead and have fun. I guess I should be comparing it to the integral from 2 to infinity of 1 over x ln x dx. How about now using the limit of b approach to infinity, 2 to b of 1 over x ln x dx. How in the world do I do the derivative here? Oh boy, remember substitution rule. Oh yeah, I think this works well. Dx equals to x du. Remember all this lovely stuff? This then just becomes 1 over u. Dx becomes x du, which cancels out with the x in the denominator, which means you're integrating 1 over u, which is just ln of u, which is really just ln of x. That's the integral. We still have the limit as b approaches to infinity, and you're going to evaluate this from 2 to b. So you get limit b approach to infinity ln of ln b minus ln of ln 2. Ln b, when b approaches to infinity, this just becomes infinity. Ln of infinity is still infinity, so we know this diverges. I'm not going to write that big long blurb again, but I'll just say therefore by the integral test, and I'm just going to use IT to represent integral test, the series that we're talking about here must also diverge. There we have it. Okay, I'd like you to do the same thing for examples 3, 4, and 5. Once again, I am asking you to use the integral test. Once again, you should be checking to see if they're positive, continuous, and decreasing for all x values bigger than or equal to 1. I'll tell you they are. So can you just go ahead and do the same setup of the improper integral from 1 to infinity and see these 3 examples to determine if they're convergent or divergent. I believe you can do this on your own, so I won't be talking anymore because I know you hate my voice, but you should be able to work on it yourself, and I will write down my solution as well. So why don't you pause the video and try this on your own. See you in a few minutes. I guess I should have written down this first day. Ln of infinity, this diverges, so this is infinity, therefore by the integral test, the sum of n equals to 1 to infinity of 1 over n diverges. Next, this is the integral from 1 to infinity of 1 over, and let me rewrite this as x to the power of half. I can also write this as x to the power of negative half. Wow, simple integral. Add 1 to the exponent, which is 1/2. Divide by a new exponent. Plug in a 2, or multiply it by 2. It's time to plug in numbers and values. So 2b to the 1/2 minus 2 times 1 to the 1/2. B to the 1/2 with infinity. This part is also infinity. Minus 2, that's still infinity. This also diverges. So therefore, by the integral test, the sum of n equals to 1 to infinity of root, or 1 over root n, also diverges. And if the first two diverge, the pattern says the last one should diverge. Right? Let's see. 1 to infinity, 1 over x squared dx. Limits b approach to infinity, 1 to b, x to the negative 2 dx, x to the negative 1 over negative 1, evaluated from 1 over b. After doing the integral, our integral is easy now. This is the same thing, I guess, as negative 1 over b minus negative 1. I still have the limit of b approaching infinity. Notice this time when I plug in infinity, this becomes 0 plus 1. That's 1. Wow. So by the integral test, what do we see here? The sum of n equals to 1 to infinity of 1 over n squared converges. Did you get the same answers as me? If you did, give yourself a pat on the back, and that's excellent. And it leads to our next page. Please turn with me. What's this thing called a P-series? A P-series has a special form. It says if P is a positive constant, so I have it as a positive exponent, okay? Then the sum of n equals to 1 to infinity of anything in the form of 1 over n to the power of p. So it's something to the power of p. That's what we call the P series, where it's like 1 over 1 to the power of p plus 2 to the power of p and so on. We call these all P series. And the last three examples we did are all called P series because the p value, or sorry, because it always had n to some sort of power of p. If you look back, and I think example number 3, the power of p was 1, right? In number 4, the power of p was 1/2, and in number 5, the power of p was 2. So, by the P series tests, and hopefully what you could see from the 3 examples we did before, is that if the p value is bigger than 1, this is example number 5, then the P series will always converge. And if the p value is between 0 and less than or equal to 1, careful of that equal to, then this series diverges. And that's examples 3 and 4. Notice when p equals to 1, that's a series with a special name. It's called the harmonic series. And if you want to figure out why it's called the harmonic series, look it up on Google and tell me your answer when you get back to class. Okay? The sum, once again, when p equals to 1, is just really n to the power of 1, which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. Okay? So if you can rewrite the series in this form of 1 over n to the power of p as a P series, then you can just use the P series test and not the integral test to help you determine if it's convergent or divergent. So I hope you can take a look at example 6 and 7 and write it as a P series, and then just look at that P value to determine if it's convergent or divergent. So in example number 6, what would be the value of P? I hope you can see that as a summation. This is the sum from 1 to n, and it's 1 over n, and the question is, what is the value of P? Well, notice it's 2, and then root 2, 3, and then root 3, 4, and then root 4, so it's like n and root n. That would be n to the power of 1 and n to the power of half. add them together, that's n to the power of 3 over 2. Since the p-value here is equal to 3 over 2, and it's greater than 1, I'll say pi the p-series test. The series, you got it, converges. Do the same thing for number 7. I think you can try that yourself. So I'll once again be quiet. Whoa. That's the same thing as 9 over 3, right? That simplifies to negative 2 over 3. Sorry, a bit lazy here. Yucky. I told you I wouldn't talk, so I'm not going to, and I still am. Notice now, if I write this as the form of 1 over n to the power of p, p in this case now is equal to 2/3. It's less than 1, so by the p-series test, the PST, the series must diverge. That's it. Welcome to the integral test and the p-series test. 2 more tests for convergence and divergence that you need to put in your head.